Yeah, took a little vacation. It's good. Everything's good. Yeah, hung out with wifey and the baby. So we have what earnings season coming up very shortly. Lily's at $1,000. Wow. Guess who's back? You want a new challenge? Oh man. Yeah, staycation in San Francisco. Buongiorno. Yeah, so Lily's at unbelievable $1,000 a share. Let's see here. I was gonna say I'm jet lagged, but I think jet lag is fake. It's not real. Wow, Lily doubled off the August lows. Almost doubled. Yeah, I don't think I want to do any more trading accounts. I get too swept up in it, and my main job is not to trade. Um, but I'd consider it. I mean, I'll do whatever makes everybody happy. I think I could have a portfolio, but I don't know how much I want to do with trading. Trading is, I just end up, glued to the screen and not really doing anything productive. And I'm trying to be productive. I also have a business to run, which is getting bigger and bigger, so that's quite taxing. And I'm also helping out on this QCLS. Check that out. I'm going to try to make an optical computer. I'm doing this all messed up. Let's see here. Oh yeah, Abivax is good morning, good morning, morning. Yeah, remember QCLS is a publicly traded company, so I certainly can't give you insider information. I don't care about public elected officials, what they buy. No, I don't think anybody does. That's pretty cringe. Well, Godel is a tool meant for people who are professional investors. And I use it to look at stocks. Doesn't mean I have to try to trade them in and out. But again, like I still think I can make investments. So QCLS is, like I said, I have to be careful about what I can say and can't say. It's like basically a brand new company. You think of it as a startup. You know, I'm pretty excited about it, obviously. Let's see if I move my face here. It's here in the corner of my screen here next to Open Door. Yeah, I think that because, so basically the journey that got me to QCLS was shorting the quantum stocks and losing a lot of money and not buying the quantum stocks and trying to figure out like why do people care about quantum computing? And obviously, you know, my thesis on quantum computing, people don't understand what it even is. But the success of NVIDIA, almost 5 trillion cap right now, basically, and I don't think going away anytime soon, basically is, you know, telling people that compute is important. And it's actually the most important thing in the world right now. And that was never the case. Semiconductors are never truly that important. And now they really are the linchpin of global economy. So how do we compute? I think the question is, what do we need to compute? Okay, here comes the paint. I think it's actually, we're also better off doing it like this. This is nicer on the eyes. Okay, what do we need to compute? And I guess just how, right? Oh, well, hold on. Yeah. What do we need to compute? How do you compute it? And with what computer do you compute it with? This is the question, ladies and gentlemen. And I think that this is what very few people who actually want to answer this question go through. The people that want the huge return, I mean, think about NVIDIA, let's do it in the corner here, 5 trillion. That means that you can make 1,000x even with a 5 billion cap, right? Even with a 5 billion cap, you could actually still catch 1,000x. So that's why if you look at a D-Wave or an IonQ or whatever, why not, right? I don't need to know what quantum is. I want the chance at the 1,000x. It's okay if I lose everything. The 1,000x is worth it to have a little bit in, or a lot of it in if you're greedy. And so that's the theory, is like, okay, NVIDIA's 5 trillion. I need a new kind of computer. What are the new kinds of computer stocks I can buy? Here's some of them. Okay, but what do we actually need to compute? And I think, you know, the simple answer, of course, is AI. But what is AI? And it's something called a matrix multiplication, or a matmul, or sometimes called a MAC, multiply, accumulate. And so how do you do that? Well, there's a number of algorithms to do this, but most algorithms are in the n cubed. So the size of the matrix is n, and it takes n cubed steps to compute a matrix multiply, assuming the matrices are the same shape. And we do this right now with GPUs. And I'm just going to say, yeah, I'm just going to put the complexity time here. And then maybe I'll actually do this too. Let me see. I'm going to erase the explanation as to why do people care about quantum is because everyone wants to catch the next big thing, the next NVIDIA. And to catch the next NVIDIA, I think you got to know something about computers. You might be able to catch the hype, but to catch the actual success, let's see what this looks like. All right, I'm sort of done erasing here, I think. Do I have to color this in? Let's see. Okay, cool. And so now we're going to do, I guess we can do like clock speeds and cores. So clock speed of GPUs, 2 gigahertz. I guess we could do power too. This is getting to be very big. Okay. Sorry for that. Cores and I guess energy is becoming a more important thing, right? So let's say this bad boy is what, 1,000 watts? 1 kilowatt. It's got 15,000 cores, roughly 16,000. And those cores are running at 2 gigahertz. So we can even do it tops or flops, and you got to do it versus watts. Okay, so AI is the main thing, right? This is 99% of computer workloads right now. Anybody who tells you otherwise is lying to you. This is the most important thing. And you know that, right? You know that. You know that's what people are buying these computers for. You've seen the Elon. You've seen the OpenAI. All right, now let's do quantum. There is no complexity speed up for quantum with matrix multiplications unless you're talking about Grovers, which has not been implemented. And Grovers would not apply to these matrix multiplications. Let's see if ChatGPT, or should I use Gemini, or should I use Grok? Let me see here. Open guest profile, chatgpt.com. Would quantum computers have a complexity speed up for the matrix multiplications typically used in today's AI workloads? Not in the way people hope. Should we listen? I think I'd like to listen. AI is good at speaking these days. Do I have to log in to listen to this?
Hi there.
All right, well, I'll read it to you. Quantum computers don't currently offer generic, substantial asymptotic speedup for large, dense, that's the key word, matmols at the core of today's neural networks. However, there are specialized settings and algorithmic twists where they might help. Matmol speedup means O of n to the 2.373. Now, this is a galaxy algorithm. Most matmols are happening at O n to the third. Technically, you could do them this fast, but it's not usually what happens.
In most practical AI workloads, matrices are large, dense, and irregular. Do quantum computers speed up generic dense matrix multiplication? No known general quantum algorithm provides a substantial, exponential, or even strong polynomial asymptotic improvement for arbitrary dense matmoles. Quantum algorithms excel when they leverage interference and superposition, like Grover's for quadratic speedup of unstructured search, but dense matmoles don't map cleanly into those problems. So when I said Grover's, I meant HHL, for what it's worth. There are quantum approaches to linear algebra, but you can see they don't really apply here. There is a quantum linear systems algorithm called HHL, which I mentioned earlier. That's what I meant when I meant Grover. Grover is a search algorithm. HHL is a matmole algorithm. But this sort of requires this sparse well-conditioned matrix. Does not work out for quantum, and it wouldn't work out anyway, even if it applied, which we'll talk about later. But the answer is no. No, 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 no. No matmole speed up with quantum. So you're at the same complexity class, but instead of 2 gigahertz, you're at 1 megahertz. It's pretty slow. And that's maybe being generous. You have 1 core instead of 15,000, and God knows how many watts you need to do the cryogenics. But if you're not doing the cryogenics, you still need wattage to do the pressure chamber. But let's be nice and just say it's 100 watts. But you lose virtually on everything here. So photonics, this is where it gets interesting. This is why I'm interested in photonic computing. And I'll sort of tell you more shortly. But theoretically, you may be able to do a matmole in linear time, which would be pretty incredible. The clock speeds are all over the place. I would say that the bare minimum, they're the same as GPUs. But because it's the speed of light, theoretically, you can get to 100 terahertz. You're still dealing with 1 core. That's just sort of the nature of of most computers, as opposed to the way GPUs are built. And you've got pretty low energy footprint. So that's the idea, is that this linear time versus exponential time, or really it's polynomial time, I should say. But it's a n cubed. Linear time, or even O of 1, depending on how you look at it. I'd be more conservative and call it 2n plus 1, because you have to set up the matrices. That's what makes photonic exciting. Now, there's a lot of problems with photonic. That's why we don't have them yet. But, hopefully my goal for QCLS is that we can build this over time. And it could take, a decade, but that's okay, because we're seeing companies like Grok. Grok got acquired for $20 billion by NVIDIA over the holiday. I'm sure you guys saw. So the goal here is to sort of make a fully optic quantum computer. There's a lot of problems with this. So you sort of start off with a laser. I don't know what the right way to draw a laser is, but I have to get my drawing skills up to speed. But you got a laser. You have different optical components. Now here's sort of the trick. You have to do a digital to analog conversion here. Okay, you have we'll talk about what's in the box in a second, but assume it's a black box. And then here you're doing your ADC. And these 2 steps are the problem, because assuming in here you have resonators and mirrors and all kinds of things that, in fact, you have 2 focal lenses perhaps. It's called the 4F model. And it can do a Fourier transform and other convolutions and things like that. Assume there's some crazy things that happen like that. And you can take, 2 matrices. And get the matrix back out. And inside here, let's say this process is happening extremely fast.
Now, the problem is that this DAC step and this ADC step do not happen fast. And there's more, don't worry, there's more problems we have to solve. But these two steps bother me a lot. So I have a plan for those two steps, and I'm probably not going to go into too much detail on the technology and how we solve, or how we might solve the problem. I think it's not going to be easy. But these traditionally don't go that fast. So if you have to go from digital ones and zeros to light, which is wavelengths, and then you also need to go from wavelengths back to ones and zeros, these conversion steps kind of ruin, in my opinion, a bit of the fun. But there's a fundamental bigger problem, which is something called nonlinearity. And nonlinearity is, the idea of nonlinearity is that you need nonlinear elements to actually do real compute. One of them, in the case of AI, is things like softmax and ReLU and things like that, the activation functions, because the matrix multiplications are actually linear. You can, in fact, shine a light, depending on how you set up your mirrors, and how to do, like I said, an O of 1 matmul, which is kind of amazing. But what about the activation functions? We all know are softmax, ReLU, GelU, tanh, etc. from neural networks. These guys need a non-linear response. You know, do we know what these activation functions are? I think you guys know. Let's take some pictures. Here's one from LinkedIn. So ReLU is just the max. So ReLU is the biggest value other than zero, non-zero value. 0 if they're all negative. There's GelU. I've never seen PreLU, to be honest. Soft plus, soft max, sigmoid, etc. tanh, lots of different ways to manipulate data. But at the end of the day, these are hard to do with optical. And in general, nonlinearity is one of the most important things in computing. So how do you do nonlinearity? Well, there's about 5 different avenues, and I think that each of them have their drawbacks and advantages. But those are the 2 questions, in my opinion, that need to be asked. You know, one, you know, so anyway, taking a step back, I guess, and zooming out. Yeah, question one is nonlinearity. Question 2 is the ADC DAC, which some optical computing experts I talk to don't think this is a big problem, but I do. So keep your eye on that. Nonlinearity is traditionally thought of as the biggest problem. Data loading, which I guess is sort of here, but it's not exactly only in there. So if you came up with an all optical, so you got rid of this step and got rid of this step, you still need to load and adjust. I guess you could say adjusting weights. So taking a step back, you know, manufacturing is sort of another thing here. You need to be able to beat the costs of NVIDIA. But to take a step back, I think that the 20-year mission, the 5, 10, 20-year mission companies are okay. I think that, you know, certainly quantum computing is one of them. A lot of the AI, like OpenAI, was supposed to be a non-for-profit that had a long-term mission to do AI, and it obviously changed. It sort of stumbled upon something really big and is now a $1 trillion company. But it started out as more of a think tank. And I think if you told me that, like, okay, you wanted to beat NVIDIA and it was going to take you, I don't know, 20 years, would I have not bought the stock? So if this is NVIDIA and you know it's going to end up here,
but this is a 20-year time frame. Now, what's nice about NVIDIA is you got to see, you know, the price go up along the way. But if it just meandered and then went up, then you'd sort of have a different, a different situation, but you'd still, I think, be interested in investing. Obviously, we all want to invest on this date, but the market, NVIDIA's chart looks a little different, actually. It looks more like this. I'll do it in blue. It actually does look pretty parabolic. It looks parabolic until it goes really parabolic. So anyway, the thing about NVIDIA is they had a business in the gaming GPU space until they hit the inflection point with AI, and nobody knew that inflection point would come around. The difference today is you have a 5 trillion market cap, and we know what people want. People want a much faster matmul. And that much faster matmul has to come from somewhere. We don't know where it's going to come from. Optics is my bet. Grok's bet was something called SRAM, which is really on-chip memory. So the memory is like literally on the chip in the bus. There's no bus. There's no memory, moving from the processor back and forth. The von Neumann architecture, it's all just sort of one circuit. Venezuela's UN envoy. Maduro's in my old jail cell. Pretty funny. So I guess the point is, like, unlike NVIDIA, we know what the market wants, and maybe quantum's like here. And the race is to who's going to replace all this compute. Because I don't think we're going to have data centers covering the earth like CoreWeave and all of these other companies, Nebius, data centers on the moon. I think that's all nonsense. I think we're just going to make faster computers. And NVIDIA is not going to, by the way, slow down. My biggest worry is actually NVIDIA. It's not other technology or other companies. It's just more NVIDIA, faster NVIDIA. So I want to throw out a couple other crazy ideas. So, like, what else could come out of the woodwork? So I think the first is optics, and I honestly think there's no competition. But the second could be memristors. TSMC actually had a paper. I'll show you the paper. Compute and memory paper. And it includes SRAM, which is kind of neat. Let me see if if this is the right one or not. I don't think this is the right one. It might be. This is not the right one. This is it. Yeah, here it is. Okay, so I think it was the paper I showed you. It was just, I didn't look slowly enough. Well, I'll find it. But it's an interesting architecture. I think they don't call it an emristor. Or here it is. Maybe. Nope. That's Ulick. We know Ulick, right, guys?
By the way, all the interesting technology here is like almost completely Chinese, which is a little crazy. I think this is it. But I have to... Yeah, this is it. Do you guys like this new Google style? All right, so here's the paper I was discussing. Sorry, it took a little while to find. You can see it's all Taiwan Semi authors. Let's see if I can get my... I don't know if you missed any of this guy, but... All right, so this is a Taiwan Semi paper. You can see the chip outlay here. This is stuff I'm still learning. It's a little hard to spend 20 years in biopharma and then look at this stuff. I know a lot of the software stuff, but still not a software god or anything, and certainly not a hardware guy at all, but learning as fast as I can. So there's SRAM buffer. So this is sort of the Grok style. And here's the memristor compute and memory. So compute and memory is this idea that, you don't want to send any data across the chip. You just want to compute in place. And that, to some extent, is a little bit of a GPU idea, but not really. Those are sort of separate parallel cores. So in essence, you can sort of see the idea here, and it's an interesting mixed sort of concept, and it's a good paper. Have a look, but I think what's going to end up happening is NVIDIA is not stupid. This is their partner, Taiwan Semiconductor. The idea of sort of using the best of both worlds could be intriguing to NVIDIA. SRAM is obviously a little bit, of a weird idea. If you've ever played with Grok or Cerebrus, you know what that's all about. Very limited space, but very, very fast speed. TPUs sort of offer more of a GPU-like balance. So we'll see how that sort of plays out. But I think optics, could if some problems are solved, could be pretty exciting. But the memristor sort of expand SRAM, I guess, make these cells bigger and bigger, which is not easy physically. There's this idea of like thermodynamic, or another way to put it, which is I'd say 4A or 5, which is analog. And here the data point is a recent investment announced. Really interesting situation. Unconventional. These guys raised $500 million at a $5 billion pre. Again, the idea here, this is a brand new company. Just started literally. And there's some other companies doing full optical computing. Probably the most interesting is Lightelligence. But there's many others, including Light Matter. And I have a whole list of them they're all private, for what it's worth. So at $5 billion, the unconventional brand new company raising $500 million, because again, you can get to $5 trillion if you solve this problem. You might even get to more than that. So why not? If this actually pans out, it doesn't matter whether they're paid $5 billion or whatever. Who cares, right?
It's a huge reward regardless. Now, I do care what I pay, but that's another story. The wild card that I kind of like is biological compute. Now, this is a bit crazy because we don't know how to really program these yet, but there are some companies that are interesting here, like Final Spark. And then what's the other company called? I always forget their name. I was bothering the CEO. Cortical. So these guys grow neurons on a dish. Final Spark does something similar. So use cells to compute. The brain only needs 20 watts. NVIDIA needs 1,000. And there's other approaches. This is not exhaustive. I have a more exhaustive list that I've been keeping. But, the race is on. What's the next computer? Oh, yeah, we forgot the most important one of all, quantum. Of course, any viewer of this channel knows that quantum can't help you. No clock speed, no cores, no algos. That's all you got to say. Why care about quantum? Well, there's one reason. In this scenario, you can actually get, let's use this framework. You see the AI Mac up there. Let's do the same thing here. Let's see. So AI is 99% of workloads. We're going to do Shor's. Well, let's actually do decryption, which is, I would say, less than, it wouldn't be number 2. It wouldn't even be in the top 100, I think. What percent of compute time is spent on matrix multiplications versus decryption routines? It's not even absurdly close. But for GPUs, this is an exponential, right? So this is sort of 2 to the n. For photonics, same thing. We don't have an algorithmic speedup, 2 to the n. But amazingly, for quantum, this becomes 3n squared or cubed, which is, massive, massive W. The clock speeds are all still the same. 2 gigahertz, 2 gigahertz, 1 megahertz. The cores are all still the same, 16K, 1 and 1. And the wattage is still the same, 1,000 watts, 100 watts, 100 watts. But the clear winner is here because the algorithmic speedup. But unfortunately, that algorithmic speedup doesn't show up anywhere else. You have something called Grover's, which is this weird unstructured search thing. And there you go from, you just get a quadratic speedup. You go from n to root of n, which is not so exciting because you can just do that with GPU. And then you have HHL, which is also, in essence, modified Grover's. And you basically get the same thing. So these two are not, the juice is not worth the squeeze. Nobody does that much sparse matrix multiplication or unstructured search that it's necessary. And you still have to set up the quantum states and all of that. I'm not giving you any of the sort of things that come with, like setup time and superposition time, all of those things, that sort of make quantum really difficult. So you can't just load in the data really fast yet. There's lots of issues where, it just wouldn't make sense. The only place where you get that lightning speed is with Shor's and decryption. So quantum is sort of a dead end. Now, if you think, I just don't know how you can make a bull case on quantum. It just doesn't stand a reason. There's no place that I can tell. At the same time, part of the pitch on quantum is we don't know what algorithms may come. When people work on algorithms a lot, we still don't know, sort of any good ideas on quantum algorithms, but I don't know. I wouldn't base my investment thesis on hope. I'd rather have an engineering challenge. Engineering challenges are solvable.
making new quantum algorithms is very difficult. And the White House, interestingly, has said publicly, let's just say, close this now, has said that they don't want to invest in quantum computing companies. They want to invest in quantum information science. So to the extent they want to help in the quantum world, they want to help figure out how to make these machines useful. And it's very smart of them to do that because it doesn't cost much to fund some mathematicians and some physicists to sit and think all day, as opposed to build a machine that doesn't do anything. So very, very smart on the White House's part. They have David Sachs and some other smart people there. Who understand technology and understand that there's no point in building a quantum computer if you don't have a good quantum algorithm. Again, decryption aside. So excited about new kinds of compute. Obviously, silicon's also not going anywhere. Like I said earlier, there's a lot of things you could do with today's machines that could potentially get you some of the way there. There's co-packaged optics. Again, most of this for interconnects. In fact, the 3 optic stocks that I look at, these are sort of all interconnect companies, Light, Coherent, and Fabrinet, are all down 5 to 10% today. Very interesting. So anyway, that's kind of what's going on with that. Oh, I'm sorry about the audio. Like I said, I don't have a professional